In this video, I'm going to show you how to create the flanger effect using Max MSP and Gen. Flanger is an audio effect with a very characteristic whooshy, swooshy, jet-like sound. And even though this effect makes use of very simple components like delay and a few parameters, it is possible to generate a lot of variety from this simple algorithm thanks to its parameters like rate, depth, minimum delay, and feedback. And even though this effect was used most prominently in the last few decades, I think this is not only a very good introduction in creating audio effects using Gen, but also exploring generative possible timbres by means of tried and tested audio effects. Let's see how we can implement such an effect. Here is the plan. We are going to use this block diagram from the book Audio Processes by David Creasy and apply it in the world of Gen tilde, in order to process the incoming audio signal with this algorithm to create the flanger effect. The theory behind the flanger effect is fairly simple. We are taking our audio input, we are applying a very tiny amount of varying delay on it, so the delay is constantly changing, and this constantly changing tiny amount of delay, so really a delay in milliseconds or even a few samples, is going to apply this constantly shifting harmonic filter on the incoming input, and this is going to create the flanger effect. Now, if you just want the effect itself quick and dirty in Max, you can go to Package Manager, download the rainbow guitar pedals, and there, in its help file or its intro screen, you can choose the flanger effect, and you can check out this patch right here. Unlocking the patch and double-clicking on rainbow after it's loaded should give you this complicated patch that essentially is a very thoroughly coded or patched stereo flanger effect. I, however, am not currently interested in how to achieve that effect as quickly as possible in Max MSP. I'm more worried about implementing this in the world of Gen. Now again, this algorithm, or this block diagram specifically, comes from the book Audio Processes, which is a book I absolutely recommend if you are interested in not only audio effects, but how these effects are created, and especially how they are created in digital signal processing systems. If you are not familiar with block diagrams, the idea is simple. A block diagram is going to describe how a signal is going to be processed by certain processes, right? Well, that comes off as weird, but yeah, so we're going to take a signal, we are going to put it through a process, certain things like addition, multiplication, delay, certain parameters, and what we are going to get is a certain effect applied onto that signal. Now, to do this in Max MSP, we need to be able to read this block diagram. Luckily, it is fairly simple in this case. The input and the output is, well, you guessed it, the input and the output. The plus signs are addition, so these different arrows, which imply different audio signals, are going to be summed up together. The X is multiplication. Here, right before the output, we are multiplying the signal by 0.5, meaning we are halving it, or we are dividing it by 2. These wibbly knobs here are parameters. So the rate, depth, minimum delay, and the feedback gain are going to be parameters which we can control from outside of the effect. And this squiggly line here is an LFO. It's an oscillator. It's a oscillator whose values we are going to use to modify parts of our algorithm and make sure we are getting this shimmying, constantly shifting filter effect in our flanger. Okay, here I have a basic setup. The audio, some default audio samples, they're going through Gen. If I double click on Gen, you'll see that there's nothing in here. The results, whoops, there we go. The result is going to go through live.gain. So we're going to kind of gain scale this to make sure it's not too loud or too soft. And that is going to go through limit2, so a limiter to make sure we don't blow out our speakers. And then we can hear the final result. Now let's open up Gen and let's see what we can do with this current setup. Okay. Now the input and output is already defined, and this is how things work in Gen, right? In one goes to out one, and then if I play the audio, I'm going to hear the audio itself. It's going to just simply get passed through Gen. But we can start working from the end, so from the end to the beginning, from the output to the input, and I know after whatever I do here, I'm going to multiply the result by 0.5. So I can immediately put this in. I know that I'm going to add this input by the result of my delay operation. So I can also create the plus object, or also called operator in Gen, and I can create the delay object. Now, delay is going to, well, delay the incoming signals or samples by a set amount determined in samples. We can either put this in as an argument, or we can put this into the second inlet of the delay operator. The first inlet is going to be the input to delay. And that is what is happening in this block diagram, right? The input is going in. It's being added to the feedback of the delay, but I don't want to worry myself with feedback right now, so I'm just going to take the input and I'm going to put it into delay right here. And then I can take the output of delay, and that is what I add to my incoming audio signal, which I then multiply by 0.5 and send it out. So this part is, let's say, the lower third of this block diagram is fairly simple, but the fun part starts when we consider the actual delay time. So how are we going to shift this delay time? To declare these parameters in Gen, we need to use the param operator, or the param object. We can give it a name. So if I create this rate, for instance, I can create it as such, and I can give it certain attributes such as default. And let's make it, I don't know, 0.25 by default. Then min, so the minimum value, which is going to be 0.1. And then the maximum value, which is going to be 1.0. Right, now this is declared as a parameter, meaning that we can change this from outside of our Gen object, and we can refer to this value inside our patch. If we look at the block diagram again, well, we can see there is an LFO, and for simplicity's sake, I'm going to create the sine wave oscillator cycle in Gen. Notice that this does not have a tilde in Gen because the implication is that these are all audio signals, so we don't really need to put tilde at the ends of objects. These are all MSP objects or operators. Okay, so rate is going to drive the frequency of our LFO. After this, we have to declare this depth parameter. So I can create another param, depth, and then I do have to watch out with this range. Now you will notice that in this block diagram, the depth is very tiny. So it goes from 0.0001 to 0.0050. These are, in this book and in this block diagram, are in seconds, right? So this is 0.0001 seconds or 1 millisecond or something very tiny. But in MSP, in Gen, we think in terms of samples. So I'm going to be then using values that are a bit higher because I'm thinking of samples and not seconds. Right? I can make the default value, for instance, 200. I can make the minimum 10 and the maximum 500, right? These are values I can play around with later on to see which kinds of other oral effects or audio effects I can create by playing around with the Flanger settings. Okay, but this is my depth, and what happens in the block diagram? Well, we multiply the result of our oscillator by the depth, and then we add the same exact depth value to the result. What does this do? This essentially maps the incoming signal to the range of depth, more specifically to a range of 0 to the depth times 2. For instance, if you imagine that this cycle goes from -1 to 1, and let's imagine our depth is 1, what is going to happen? Well, we are going to multiply the range of -1 to 1 with 1, so we're going to get the range of -1 to 1, and then we are going to add the same value, which was 1. So then, instead of -1 to 1, we are going to have 0 to 2. And this algorithm, or this little mathematical operation, is going to make sure that the result of this oscillation is always between 0 and depth times 2. After this, we need to create another parameter, minimum delay. So param, we need to give the name of the parameter in a single word. So min delay is how I'm going to write it. This is again going to be in samples, so it's not going to be those tiny values in the block diagram. So let's give it a default of, I don't know, 0. We can change this later. Minimum can also be 0, and maximum can be, I don't know, again, 500. 500 is a nice number. And we are going to add this to the result of our depth operation, right? So whatever our depth is going to be added to our minimum delay. So this minimum delay is going to be the baseline of this oscillation. All right, and as you can see the block diagram, this whole thing goes into the delay time of our delay algorithm. So I can go to delay here and I can plug this into the second inlet right here. There we go. All right, so there's of course this big elephant in the room in the form of a feedback, but before doing that, I want to see if this already sounds any different from what we normally have. So I'm going to step outside of this patch. I'm going to save my patch, which is very important because when you're working with Gen, things might crash. And then I'm going to play drums loop. All right, I don't know if you can hear it, but there is a very obvious flanger effect in our output. It is already sounding really cool, and we haven't even added feedback yet or played around with the parameters. Great. Maybe for comparison's sake, we should also add a toggle here, so we can create another parameter. Let's name this toggle, param toggle. Let's make it by default 1, so by default this is on, and minimum is 0, maximum is 1. So we are going to use this toggle parameter as, well, the toggle of the entire effect. Right, and here is how I like to do this. I like to use the selector operator in Gen. Right, I have to give it the argument 2, which means, okay, there are going to be 2 choices, and the first inlet is going to choose which other 2 inlets, or which one of the other 2 inlets gets forwarded, which is going to be our actual output. So let's say if toggle is 0, I want the regular inputs, right? So in1 goes into the second inlet of selector. So by default, it should be this. Otherwise, if toggle is on, well, I want to get this, the output of my flanger algorithm. Of course, toggle is going to be between 0 and 1, or actually it's going to be 0 or 1, but I want 1 or 2. So 1 would be the input without any changes, so just a dry input, and 2 would be the flanger effect, right? So I can simply add 1 to my toggle parameter, trying to kind of make it fit in. There we go. And we should have a toggle. We can even see this by going into our unlocked patcher and right-clicking on the first inlet, or for now the only inlet of Gen. Now there should be a toggle choice here. If I click on this, I'm going to get this nice @RUI object, which I can then click on, go to the inspector, go to display mode, and choose checkbox. There. Now if I play the audio again, I can actually toggle the effect on and off. And I think you can very easily see which kind of effect we have created and how audible it is. And again, we haven't even added the feedback yet, which is going to be the real meat of this algorithm. So let's do that. Let's start adding in feedback. Okay, now feedback is a dangerous thing. If we leave feedback unchecked, it can start cascading and essentially destroy our speakers if it was not for this limmy right here. So we have to be very careful when we are working with feedback delay. Okay, so what is happening in the feedback portion of this block diagram? Well, the output of delay is being sent to be mixed with the input and to be sent to the output, but it is also being sent in another direction, where it is multiplied by this new parameter, feedback gain, after which it is added up together with the input, and then it is sent back into delay. Right, so we first have to declare our new parameter, param feedback. Again, we can give it a default. Notice the default is not 0, but minus 0.95. Now, this is where we have to be very careful. If feedback is 1 or minus 1, which means that the phase is going to be inverted, well, this feedback is going to happen again and again and again and again, and is never going to go away. So we are just going to be adding the result of delay onto itself over and over and over and over again, which is going to get very unpleasant very quick. So we have to make sure that we multiply the signal we are feeding back into the system by a value lower than 0 or higher than a value lower than 1 or higher than minus 1. Or we can multiply it by 0, which means there is going to be no feedback. Anyway, going back into our parameter, so the default, well, let's make it 0, right? Let's make its minimum value minus 0.95 and its maximum possible value 0.95. There we go. Okay, now we can take this delay and we can multiply it by feedback. Right, and this is what we want to plug back into delay. But I believe we have to tell the object delay that we are going to be using feedback for this to work well. So we have to give it the attribute feedback1 to say that, yeah, this object can receive feedback. So the algorithm inside Gen, that hidden algorithm, kind of fixes itself in that way. And while we are at it, while we are giving attributes to delay, we can also maybe give it interp linear. So we can set an interpolation mode because we are going to be constantly shifting between different delay amounts. And if this delay amount is between two sample values, so if it's between 1 or 2 or 3 samples, there is interpolation applied to the delay to make sure there are no clicks or pops or, those unwanted oral effects. Okay, so delay at feedback1 at interp linear. And now we can take the output of delay, we can multiply it by our feedback value. And looking at our block diagram again, we can add this to our input, and this will be the main input of delay. So now in1 does not simply go in delay. No, it is added up with the delayed feedback signal, and that goes into delay. So in1 added up with the feedback goes into delay. The result is multiplied by feedback, added up by the input, goes back into delay, and so on and so on. Maybe in order to show that this feedback is something special, I can click on this patch cord, right click it, choose color, and give it a nice red color. So we know that this specific connection is special and is a part of a feedback in our algorithm. All right, so again, save the patch, and I can now play around with all of my parameters, right? So I can right click the inlet of Gen and I can choose rates. I can choose, let's see, feedback. I can choose depth. And I think that's all. I have my rates, I have my depths. And I also need, let's see, minimum delay. All right, I got my depth, I got my minimum delay, and I got my feedback. So these are all of my settings. So let's start playing around with these guys. All right, sounding as it normally does. So I can lock the patch and change the rate. I can play around with the depth. I can even give it a minimum delay. But I think the fun part is going to begin when I start playing with feedback. As you can see, changing the feedback has an immediate effect on the timbre of the sound. I believe it adds a harsher filter in the incoming sound. And we can even go into the negatives with the feedback. And if you have a lower rate, then this flanger effect is going to be more subtle and it's going to spread over time. But we don't have to limit ourselves with this specific rate. If I go back into Gen, I can actually remove this max attribute from my rate parameter. So I can go as high as I want and I can turn this into a weird form of synthesis. So back here, if I go higher than 1, we can create really crazy sounding effects. Let's try it with, I don't know, walking bass. Look at this beautiful sound. If I go again back to a very low value and crank up that feedback, can get all kinds of different variations. Beautiful sound. Okay, one more thing to do. Let's actually make the stereo. Right now this is just a mono flanger effect, which is nice. If we want, we can just literally copy this, apply the same parameters, and have stereo, but I find it more beautiful to have a single gen patch, which acts as a stereo audio effect. Okay, let's see. So we have our out 1. Well, then in my gen, I need to declare an out 2, right? So this is going to be the right channel. What we have so far is the left channel. Then we're going to have the right channel. The input, however, is going to remain mono. Or, no, I changed my mind. Let's also make that stereo. So there's going to be in 2. Now, this is very simple because I can simply copy this entire algorithm. So I can choose the entirety of my algorithm, or almost the entirety of my algorithm, copy and paste this. And then I can simply substitute in 1 with in 2, and now the exact same thing is being applied. Here's the trick though. If I'm applying the exact same thing, I'm just going to hear the exact same thing. So I am going to add a subtle change to my rate parameter for the right channel of my flanger algorithm. So right now this is going to be, some value between 0.1 and infinity. The default is 0.25, but I'm just going to add, let's say 0.70 to this rate, right? So whatever the rate is, it's going to be that plus 0.17, and then it's going to go into cycle, which means there is going to be a subtle difference between what's happening on the left side and what is happening on the left side, on the right side. If you want, you can even change the other parameters ever so slightly, ever so subtly, to create an even stronger difference between the two. Now, to make sure toggle works in the same way, I'm going to take selector 2 as well, put it here, but I'm going to make sure these are controlled by the same toggle parameter value. Right, so the same toggle, if it's off, then we get choice 1, in 2. If it's on, then we get choice 2, which is going to be our flanger algorithm. Okay, so again, the exact same thing, only we have a new into, a new out 2, and we have a slight offset to our rate parameter here, just to make sure that there's a tiny amount of difference. Okay, and as you can see, Gen is a very smart object. It immediately understands what needs to be done and creates new inlets and outlets. So we can just plug the same inlet to this, plug the same audio signal to the second inlet, and take the second outlet and treat that as our second audio channel. Now let's see if this sounds any different. Oh yes. It's a very small difference, but this immediately creates a beautiful stereo effect. Let's play around with this a bit more. We can lower the depth. So now it's a little wobble. I can listen to feedback. So now it's not very, tin FM synthesis-like, but it's more subtle. The flanger effect is more subtle. I can then lower the rate itself too. Go to, let's say, minus 0.5 and increase the depth a bit. There we go. I'm sure that you're going to come up with some cool applications of the simple flanger effect just by changing the algorithm, tweaking the parameters, and maybe adding a generative system or two. In any case, enjoy creating beautiful and fun things, and thank you for watching.